Hello everyone, Mr. Boltri here, bringing you video 1.4, in which we are going to be talking about the big four equations for uniformly accelerated motion. I'm going to go through some terminology, fly through the introduction of the equations, talk about why they're important, and then we're going to go through one by one where the equations came from. So first, some terminology. Up until this point, I've been using the phrase constant velocity. But in the AP materials, you're probably going to be seeing the words uniform motion, or the abbreviation UM. And that just means exactly the same thing, uniform, constant motion, velocity. Uniform motion is the same as constant velocity. Also, I've been saying constant acceleration, and you might see UAM, or uniformly accelerated motion. They mean the same thing, and I'm going to try to use them interchangeably and make sure to incorporate both. UAM, constant acceleration, same thing. So then, when we talk about the big four equations of UAM, uniformly accelerated motion, there's a huge rule that you need to keep in mind anytime you use any of these big four equations. And that is that in order to use any of the equations, the object must be experiencing uniformly accelerated motion. To say that another way, the object must be experiencing one constant acceleration. If it is experiencing more than one constant acceleration, then it is not experiencing uniformly accelerated motion, and you cannot use these equations. Or if the object's acceleration is changing, then you cannot use the equations. The results will not match what actually happens, and that's a very common trap that the AP likes to use, is they like to give you a problem in which you might be tempted to use these big four equations, but it might have more than one constant acceleration or a changing acceleration. In both of those circumstances, it's not okay to use these big four equations. So now, let me introduce you to the big four equations. Kind of the order is arbitrary. I might call them 1, 2, 3, and 4, but that's just a completely arbitrary order. Just to run through the meanings of all the terms, we have final velocity equals initial velocity plus acceleration times change in time. That's a change in position, equals initial velocity times change in time, plus 1/2 times the acceleration times the change in time squared. Number 3 is change in position equals 1/2 times the sum of the final and initial velocities times the change in time. And the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in position. So those are our big four equations. And on the left, you'll notice that that's kind of my notation, the notation that I'm used to, that I learned on. And let me show you AP's notation and just point out some of the subtle differences. These are, by the way, the exact same equations. You can use either, you can use both. I will try to use both. I might tend to use the ones on the left a little bit more than the ones on the right, because those are the ones that I am used to. But I will try to use both because these are the ones that you will see on the AP formula sheet. I think I just like the notation of this better. I like the subscript F's and subscript I's. I like the delta notation, but they are both equally valid and equally correct to use. So to draw attention to some of the big differences, the first big difference is this third equation is not on the formula sheet. And I don't know why, but I'll show you in a minute why it's so useful and important. So it's one of the ones that's worth committing to memory. A couple other differences in notation. They, instead of using the subscript F and subscript I, things are assumed to be final, like this is a final velocity, final position, unless it has the naught or 0, V naught subscript, and that's just their way of saying initial velocity. They also don't use the delta notation, which for me is just change, but for them, they assume that the time starts at 0, so this is just final time minus 0, and so they kind of circumvent the need for the delta notation there. And again, avoiding that delta notation, this is final position minus initial position, which is all that is meant by the delta x over here and the delta x over here. So those are just some of the differences that you'll see between the notation that is familiar to me and the notation that you will see on the AP formula sheet, which, let me draw your attention to the top left of the AP formula sheet, which is where you will see the 3 of the big four equations. And that's kind of the first chunk that we are taking out of the AP formula sheet. So now, to talk about the equation explanation, I want to answer the question, why are equations useful? Because up until this point, we've been solving problems using mostly a graphical approach. You find the area of a VT graph, the slopes and areas all day. And it's really good to build that conceptual foundation. But once we get really good at that, it might be more efficient to use a formula that accomplishes the same task than to have to sketch out a graph, which sometimes you have to try to be super accurate with your graphs. It's sometimes just more efficient to use a formula and less prone to mistakes. And the AP exam is kind of all about doing things efficiently to maximize your time in other places. So then, well, why do we need the big four? Why is it not the big three or the big five? Like what's going on with that? So in order to think about that, we have to think about, well, what are the variables that are going on in a kinematics constant acceleration UAM problem? And hopefully you listed at least several of these, including the position, the change in position, the change in velocity, the acceleration, and the change in time. So knowing those and thinking about the big four equations, hopefully you notice some correlation between them. And what's actually going on here is that in each of these four equations, we are missing one of the major components of the problem. So for example, if you're given a problem and asked, I don't know, to solve for initial velocity and told the final velocity, the acceleration, and the change in time, you'll notice that you're given no information about what's going on with the position. No initial position, no final position, no nothing. So you can still solve this problem without ever needing to know the initial position by using this first equation. In the same way, if you're given a problem where you're not told anything about the final velocity, you never need to know it, and you're still able to solve for all the other variables. You can solve for everything without ever needing to know the acceleration, so long as you know at least three other things. And likewise, you can solve for everything without needing to know the change in time, as long as you know three of the other variables. So these four equations allow us to solve for anything if we're only given three variables, which is a really powerful tool, and why I think it's so important that we have the big four and that you memorize this third one, so you're not ever in a situation where you can't solve for an unknown quantity if you're only given three of the known quantities. So the next thing I want to do is I want to go through each of the equations one at a time and give you an approximate sense of where they came from. Hopefully I'm not going to spend a long time on each one, or else this would be a really long and unbearable video, but we'll go pretty quickly through each of the equations, because I think it's really important that if you're going to use an equation, you understand where it came from. And you don't have to memorize this. I just kind of want you to have been exposed to it and understand it just a little bit. So this first one, we have a change in velocity, acceleration, and change in time. And so then that gets me thinking about a velocity versus time graph. Because where do we see acceleration on a velocity versus time graph? Well, it's in the slope, and we know slope is rise over run. So change in v over change in t equals acceleration. And then knowing that change in velocity is final velocity minus initial velocity, and with some algebra rearrangement, boom, we have equation number one. It's literally just the slope of a VT graph. This equation is basically the definition of acceleration. And don't forget that if this VT graph is not linear, then this equation falls apart. If it's a curvy VT graph, or if it has two different slopes, this equation doesn't work anymore because it is not meeting the criteria for uniformly accelerated motion. Now, for this one, we're talking about displacement, time, and acceleration. Makes me still think of a velocity versus time graph, because where do we see displacement or change in position on a velocity versus time graph? Hopefully you remember that it's the area, and there are a couple different ways that you can find the area, but the first that comes to my mind is to break that shape into a rectangle and a triangle. So we know the formula for the area of a rectangle is length times width. Formula for the area of a triangle is 1/2 times the base times the height. So substituting in delta t, we're relevant, initial velocity, and this is going to be final velocity minus initial velocity, which is just change in velocity, we get this equation. So this equation looks a lot like one of the big four, except the difference is instead of having an a delta t squared, we have a delta v delta t. So then we need to use what we know from the first equation, which is that change in velocity equals acceleration times change in time. Just do a variable substitution, and then we get equation number 2. For equation number 3, comes from a very similar place, VT graph, and we're still talking about displacement, so it's still the area of the VT graph. But this time, instead of breaking it into a rectangle and triangle, we're going to think all the way back to geometry class. And we're going to remember that the area for a trapezoid is 1/2 times the sum of the bases times the height. So if we think about the height, it's kind of like a trapezoid on its side, right? If we think about the height as the change in time, and each base of the trapezoid as one of the velocities, initial and final, then we can find the area of the trapezoid by, and finding the area of the trapezoid just gives us equation number 3. And again, I just want to highlight that if this line is not linear, if this is curvy, then we can no longer use the area of a trapezoid because it's not a trapezoid anymore, and therefore we cannot use the equation anymore. So again, I just cannot emphasize this enough. Anytime you use one of these equations, it has to be a linear VT graph, it has to be one constant acceleration. And the last equation, this is kind of like the crazy one, and there is a graphical approach, but it involves like quadratic functions and then linearization, and the easier way for me to remember where this equation comes from is, well, what is so special about this equation in the first place? This equation allows us to solve for a problem if we're given no information about time. All we need is some information about velocity, acceleration, and position, and then we can solve for any of the other 3 variables. So that is actually really interesting to me because you can solve for it without change in time. So we're going to take 2 of the other equations and isolate time in one of them. And then we are going to take that time, or that function for time, and then substitute it into another equation. And then just with some algebra rearrangement, which I will leave to you, we get equation number 4, which just, this is not a graphical approach, it's more of an algebraic derivation. But the reason that I show it to you is because it really reminds you that this equation is super useful because it takes time, substitutes it in, and then eliminates the need for us to have time in the equation at all. So remember, always use this rule. They will try to trick you and give you a situation in which you try to use the equation when there's not uniformly accelerated motion. So that was really, I went through that as fast as I could without going too fast, I hope, so that this video wasn't too long and unbearable or too fast. I'm trying to strike a balance there. But I'm hoping it's going to make a little bit more sense next class when we start to do problems involving the big 4 equations, and you'll see how to use them efficiently, how using them speeds up your work, and why they are useful and helpful. So looking forward to doing some practice problems with you next class. This is Mr. Boltri wrapping up the video on the big 4 equations of uniformly accelerated motion. Let me know if you have any questions, and go Bears.